Alright, there are only 2 more videos left in lecture 7, so random forests, and then in the next video we will be talking about stacking. So random forests are particularly interesting because they are among the most widely used machine learning algorithms. Okay, I already said that for gradient boosting in the last video. However, I think random forests are even more widely used than gradient boosting. I mean, gradient boosting is the approach that usually wins the competitions, but still random forests are very popular, especially in applied research areas, because they are very easy to train. So in random forests you usually don't have to worry as much about hyperparameters and things like that, or hyperparameter tuning. And also random forests are conceptually a little bit easier to understand than gradient boosting. So even though maybe the winning solution may not be the random forest, in many real-world applications of machine learning, random forests are still widely used because they almost always work very well out of the box without requiring that much tuning. Just to recap what we talked about majority voting, bagging, boosting, random forests, and then we are going to talk about stacking. So boosting will not be relevant here, but we will kind of revisit the topic of bagging when we talk about random forests. So random forests are taking the concept of bagging one step further. So in particular, you can actually think of random forests as bagging with decision trees plus random feature subsets. So it's basically bagging where we have the bootstrap sampling, and then we also add another random component, and these are the feature subsets. So what does that mean? Let me explain. But first let's briefly recap bagging. So because it has been a while ago, we talked hours and hours about boosting, so just let's briefly recap bagging, and then I will explain the new random component that the random forests add to the bagging procedure. So in bagging we talked about these bootstrap samples. So we have a training set, and then we resample the training set. So we are drawing bootstrap samples from the training set. So if we have n bootstrap samples or n rounds, we will have n models that we will be fitting, and each model is a decision tree, usually without any pruning. So actually it's I would call it a deep decision tree. It's an unpruned decision tree. So we usually don't set the maximum number of nodes. We could do that. We can set the maximum size for the tree or maximum depth, but usually in practice many people don't set it. So it's usually about very deep decision trees fit to these different bootstrap samples. And this was also the part that we can parallelize. So there's no dependency. So fitting the first decision tree on the first bootstrap sample doesn't influence the second one. They are all independent. And then we let those models during prediction make these predictions. And then the final class label is determined by majority voting in the classification case, or we can also use averaging in the regression case. So that gives us then the final prediction. So this was again the main overview of how bagging works. So random forests, they use the same concept. So they are also relying on these bootstrap samples. So each decision tree in the random forest is fit on a bootstrap sample. But in addition to that, there will also be these random feature subsets. So for random forest, you can think of bagging plus that at each node, the random forest only sees a random subset of features. So if we have a decision tree, I was just sketching it out here, like with the different nodes. So this is a decision tree that only splits 2 times. So one split is here and the other split is here. So at the first node, it will maybe see from the iris data set only the feature sepal width and petal width. So which features the random forest sees at each node, which features the decision tree sees at each node is randomly determined. So it's just a random sampling procedure where only a random subset of features will be available at each node. So instead of deciding which of the 4 features to use, like in bagging, the random forest now only has these two features to decide. So it will find a good threshold for sepal width and petal width and then decide which one to use based on maximizing the information gain. Now, then in the second node here, in the second split, it sees again a random subset of the features. And because it's random, it could be the same or it could be different ones. So here, for example, it could be just the petal length and petal width, this node that it has to decide upon. So again, the decision tree would find a good threshold for petal length and petal width. And then based on the information gain, which one maximizes the information gain, it will choose one or the other feature. And in bagging, always all the features would be considered at each node for each decision tree, because that's like how decision trees usually work. So usually decision trees see all the features. Let me write this down because it's maybe important. Usually decision trees see all features at each node. And of course, then also bagging also does that, because bagging just uses regular decision trees, for example, card decision trees. And random forests decision trees, let's say decision trees in random forest. Trees in random forests see only random subsets of features at each node. So that's the main difference between bagging and random forests, that the random forests only see these random feature subsets. Yeah, there's actually a common misconception about the random feature subset, and this mistake also happened to me back then in 2016, which is why I remember that so well, because it was kind of a weird mistake that I made, and since then I never forget this. So actually I also confused these two methods when I was teaching the machine learning workshop at SciPy in 2016. So there are two related methods. So there is, by Tin Kam Ho, the random subspace method. So this random subspace method is kind of like a random forest. However, so each tree in the random forest gets a random subset of features. So we have multiple trees, right, in the random forest, and each tree will get a random subset of the features. That's the method, the random subspace method by Tin Kam Ho. And the trademark random forest, that's the official random forest model by Leo Breiman, described here. This one is based on selecting a random subset of features at each node. So that is exactly what I explained in the previous slide. So if I, let me just draw this, if I have a set of decision trees again, say these are my decision trees in the random forest. So this is my random forest consisting of multiple decision trees. When we draw or grow these decision trees, at each node there's a random subset of features. And this is for the random forest method. And then for the random subspace method, each tree gets a random subset of features, but then at each node the same subset is used. So there's no additional randomization on a node-by-node basis. So each tree gets a random subset in the random subspace method. But in practice, most people use the trademark random forest, which works exactly like I explained in the previous slide, where each node gets a random subset of features. I just want to clarify because there can be sometimes a misconception of how the random feature subsets work. Oh, I also want to say one more addition regarding this feature subset that is selected at each node. So what should be the size of this feature subset? So how many features should be selected at each node from the pool of all the features? So in practice, the most common convention is to compute the number of features as log 2m plus 1, where m, well, I actually wrote it down here, where m is the number of input features. So if we have something like iris where m equals 4, then this one, log 2 of 4 would be 2, right? So this would be 2. In the case of iris, we would then have 3 random features at each node. So if we have a data set, let's say 16 features, 16 is 2 to the power of 4. So in the case of 16 features, this one would be 4 plus 5, this one would be 5 random features at each node. Yeah, and that is how that is usually done in random forests. But of course, the number of features at each node is also a hyperparameter. So you can change that hyperparameter, but this is usually the default value. Again, yeah, because computer scientists like log 2s. Yeah, so how does the prediction now work in a random forest? Also, that is very similar to bagging. So if we have a new data point here, let's call this data point x. This is a feature vector, right? So we have x as a feature vector, x1, x2, x3, where these are our feature values. This is then passed to each decision tree in the ensemble. Because it's an ensemble method, there are multiple decision trees, right? So here in this case, I was just drawing 3 decision trees. So it's tree 1, tree 2, and tree 3. And then depending on the feature values, it's going through the tree. So in green, I was like just highlighting an example of how the feature is passed through the tree depending on its feature values, right? Because at each node we have the decision whether it goes left or right. And we do that then for each tree, and each tree will be different. Actually, in the random forest, the trees will be even more different usually than in the bagging classifier, because now also at each node, the decision tree only has access to a random subset, whereas in bagging, each decision tree has access to the complete feature subset. But also in bagging, all the trees would be of course different because they are fit on different bootstrap samples. Now then, after the feature vector has passed through all the trees, we then obtain these predictions. So for each tree we get a value which is either the majority at the given node or the average, right? So at each node, if we have multiple training examples, let's say we have the labels 1, 1, and 2 at this node, then we would usually do a majority voting and return the label 1 if the node is not pure. And in regression, we would average, right? So for example, if at a given node in regression, we had the values, 3, 3, 4, this would be 10. The average would be then 3.33, right? So we would collect the labels from each tree. For example, let's say this node here also returns a 2 for class label prediction, and this one also returns a 2. So what goes in here is a 1, a 2, and a 2 in the classification case, and then we have another voting here, like in the majority voting classifier, to determine the final class label. So in this case, 2, 2, and 1, that would be 2, the majority. And also then in regression, we would average. So if 1.0, 2.0, and 2.0 are our values from regression, then we have 5 divided by 3, it should be 1.6767, yeah. So then for regression, the average would be 1.67 and so forth. So that's how we would combine the predictions. And in addition to that, I also want to highlight that this is done a little bit differently in Scikit-learn, in the Scikit-learn implementation. So in contrast to the original publication of the random forest algorithm, in this paper by Leo Breiman, the Scikit-learn implementation combines classifiers by averaging the probabilistic prediction instead of letting each classifier vote for a single class. So this is essentially the soft voting that I explained for the Ensemble voting classifier, the majority voting classifier. So here this slide is just from, I took this again from the majority voting slides. So if we have the jth class label, where j is the number, let's say 1 to m, if we have m class labels, or let's use c if we have c class labels, then each classifier, so we have I equals 1 to n classifiers. So if we have n classifiers, each classifier, each of these, returns c values. So they return, so each classifier, if each classifier is a row here, let's call them c1, c2, up to cn. Then we have the different class labels, right? Class label, let's call that L1, L1, L2, up to LC. These are the different class labels, right? So each classifier will return a class membership probability. For example, 0.2, 0.2, and 0.6. So they have to add up to 1, right? If so for all the classes, if we have only 3 classes here, L1 to L2, L3, then this should add up to 1. So each classifier gives us a class membership probability. So for example, the class membership probability for the first class is 20%, for the second class it's 20%, for the last third class it's 60%. And then, for example, for the second one, we may get something like 0.3, 0.4, 0.3, and maybe for this one, 0.4, 0.3, 0.3. And what we are argmaxing here is the columns. So we are looking basically at the one that has the highest column sum. So if I look at these column sums, 6, 8, this would be 0.8. This would be 7.9. And the right one here, this would be 0.9, 1.3. So the maximum value would be this one, because we are not looking at the maximum value, but the argmax for the class label index. So this would be class 3, or label 3. And then optionally, there's also this weighting parameter here. So you can also think of it as adding a weight. So the weight is per classifier. So each of those would be multiplied by weight 1, and each of these by weight 2. This is optional though. This was from the majority voting classifier, and this one would be weight 3, weight 3, weight 3. I don't think the random forest has a weight though, so you can just ignore the weight. So again, I was just copying this slide over from the majority voting classifier. Here it's more about the averaging of the probabilities. So how can we get these probabilities from a decision tree also? That's also a good question. So this probability can be, for example, approximated by the proportion, right? So if we have, let's say, this node here, and there are 3 training examples, and the training examples have, let's say, label 1, and label 2. We can approximate the class membership probability, let's say, as a probability density at that point, as 2/3 for label 2 and for label 1 actually, and 1/3 for label 2, because there are 2/3 that have label 1 and 1/3 with label 2. Okay, so that was just a recap of the soft voting. And here was another example of how we applied the soft voting, but this one was also using the weight, which is not used in random forest. So let's just skip over this one. Yeah, another interesting aspect about random forests is the feature importance that we can compute. So this is computed basically by averaging information gains. So depending on how often a feature is used in the different trees, we can compute how important a feature is, essentially. However, we will discuss this in more detail, or revisit this in more detail in the feature selection lecture, because then we can compare it directly to other feature importance methods. So yeah, but what's nice is for the random forest, we can also easily get like the feature importance. Here's a screenshot from a talk on this project where I worked on the sea lamprey, where we were interested in finding a pheromone inhibitor that I showed you earlier. So this was here from a random forest model, and we found, for example, that sulfur was most important for predicting whether a molecule is active or not, and so forth. But yeah, we will revisit that when we talk about feature selection, and then we will talk also a little bit about how the feature importance is computed in random forests, usually. And then we will also take a look at alternative methods, sequential feature selection and permutation importance measures, and so forth. So the big question is, why are random forests so widely used? And that is because they usually perform pretty well in practice. And I also explained that random forests are very similar to bagging. So what is the advantage of random forest over bagging, and why does it usually perform better in practice? And that has something to do with the loose upper bound for the generalization error. So this is explained in more detail in this paper if you want to take a look. I don't want to go over all the nitty-gritty details talked about in this paper. Just the main motivation why random forests work better than bagging. So PE stands here for the prediction error. And the prediction error is bounded as follows. It's smaller or equal to the average correlation between the trees or among the trees. You can think of it as loosely you can think of it as a measure of the similarity between trees, how similar the predictions are from the different trees, or how similar the trees are, similarity among trees. So how similar are the trees in the forest? And then also the strength of the ensemble. This is basically how good the trees are. And yeah, there is a trade-off between the similarity and how good the trees are, the performance. So if you want to, let's say, make trees more different, then you would have to randomize something, right? So let's say here first, this is also related to what we talked about in the majority voting, where we had independent errors, right? When I motivated the rationale behind ensemble methods in the majority voting video. So the more similar the models are, usually the worse, the advantage of having an ensemble, right? So we actually want different models. So the larger the similarity, the smaller the gain of having an ensemble. So a large similarity is not good. But then if we want to make all the models very different, if we have decision trees, if you think about that, then usually we have to do something random about it. And if we introduce some randomness in that, it kind of usually declines the performance, right? Because now we have like a random feature subset at each node. And with this random feature subset, maybe the optimal feature is not contained in this subset. So the tree, one particular tree based on this feature subset on the random one, is maybe not as good as a decision tree fit on the full feature subset or feature set. So the stronger the trees, actually the better. But that conflicts then with similarity. So there's a conflict between the quality of each tree and the similarity among trees. So there is a trade-off. For bagging, for example, I would say we have better performing trees because the trees don't just see the feature subset at each node, but they see the full feature set at each node. But on the other side, the trees in bagging are more similar, and there's usually a sweet spot between the two. And I would say random forests then work better than bagging because the sweet spot is more in a balance between the similarity among the trees and how good each individual tree is. Okay, and by the way, talking about the similarity, I said in the random forests we can improve the performance by having this random component, because it reduces the similarity among trees without maybe trading too much off of the actual performance of each individual tree. But you can take this to the other extreme. So if we think of bagging as a method with, let's say, better trees, but also more similar trees, then random forests have somewhat weaker trees but less similar trees. And there's a method where it's even more extreme. This is called actually it's called extremely randomized trees, but usually people call them extra trees because that's how they are implemented in Scikit-learn. So in this extra trees, we can say we have even weaker trees than in random forests, but they are even less similar. So when we think back of the equation I showed you on the previous slide, bagging, so random forest may be the sweet spot. Bagging has better trees, but the trees are also more similar. Extra trees has less similar trees than a random forest because there's another random component in there, but then each decision tree is even weaker. So in practice, random forests and extra trees do perform very similarly. Extra trees are especially also faster than random forests, but yeah, it's on the other hand of the spectrum where bagging is more towards more similar, better trees. Random forests are in the middle, and extra trees are less similar and even weaker trees. So there's like a trade-off always. So what are extra trees actually? So the random forest, random components, let's just list them again. One is basically the bootstrapping. So basically random training examples to some extent. And the other random component is the random feature subsets at each node. And the extra tree algorithm goes one step further. So instead of just saying random feature subsets at each node, it actually selects a random feature at each node. So instead of giving each node a random subset of features to choose from to find or maximize the information gain and find the best feature, it just selects a best feature for the given node. So there's no comparison between features. The only thing that happens is that the node has to find a good splitting threshold if it's a continuous feature. So it's even more random than random forests. And sometimes in practice they can perform better. But I think the main motivation behind extra trees classifiers was making them faster, because then you save time at each node because you don't have to compare different features. You only have one feature. You only have to find the threshold for one feature instead of comparing the different features. So I think the main motivation behind extra tree classifiers was really like the computational performance. But in practice, the predictive performance is also pretty good and comparable to random forests. Okay, and lastly now the code examples. So here I have again our familiar iris code. This is exactly what I used in the previous videos, just for comparison purposes, and so that we can focus on the other code and not the model data preparation code. So the random forest classifier can be imported from the Scikit-learn Ensemble submodule as usual. And then we initialize it. There are many more hyperparameters actually, like the max depth of the features, bootstrapping or not, and stuff like that. However, in practice, if you want to have the normal random forest algorithm based on unpruned decision trees, that's the way to use it. In practice, usually the larger the number of estimators, that's the number of decision trees, the better. So ideally you can even choose, I don't know, 10,000 or something if that's working on your computer. So usually the larger the better. The only reason to choose a small number of estimators is if there's a computational limitation that your computer memory or isn't enough, or it just takes too long. But I would not tune the number of estimators as a hyperparameter. So I wouldn't compare a small, medium and large number and see which one is better. I would always just choose the biggest one you can afford on your computer. And by the way, there's also, I forgot to include it here, but there's also an njobs parameter. So you can set it to 1 if you only want to use one CPU, and you can set it to -1 if you want to use all the CPUs, but you can also use it to intermediate numbers and so forth. By default, it's only using one CPU, so you don't have to actually put a number there if you only want to use one CPU, but in practice, of course, it can be faster if you use multiple CPUs. So usually in practice, I set it to -1 if I do, especially if I do grid search, especially if I have a big data set and it takes a long time. So I know, though, there can be some problems on certain Windows operating systems or certain machines running on Windows. So it doesn't work always. Some Windows computers have some problems with multiprocessing in Python. So I would just try if that works for you. If -1 works for you, I would go with it. If it doesn't work for you, then don't use multiple processors on your computer. Yeah, and for the extra trees classifier, the same concept applies. It looks exactly like the random forest classifier. You import it the same way, and then also you can set the number of estimators and so forth. And there are also additional hyperparameters, but like I said, in practice, I would only use or tune the number of estimators. I wouldn't go so far and prune the decision trees and set a maximum depth and so forth, but you can do it, of course. Okay, so that was random forests. This video was a little bit shorter than the last one because random forests are pretty cool. There's a lot of interesting stuff around random forests, interesting applications, but it's not such a complicated topic compared to boosting. And most of it we already covered in bagging anyways when we talked about bootstrap samples. So this video was hopefully a little bit shorter than the last one. So, and then the next video will be about stacking.